Hey folks, welcome to the video. Today we're going to be talking about moments of inertia. It's a quantity that measures how hard it is to rotate an object. We're also going to look at an example of a solid cylinder with uniform mass density so that we can calculate its moment of inertia and better understand what it means. Let's get into it. So today we're going to talk about moments of inertia. Moments of inertia can be understood using torque. Torque is equal to the moment of inertia times this quantity called the angular acceleration of an object. And the moment of inertia is very much like the mass in the equation F equals ma, Newton's second law. Mass is a measure of how difficult it is to move an object, and a moment of inertia is a measure of how difficult it is to rotate an object. For a point mass m, its moment of inertia from some origin is mass times the distance from that origin squared. So if we had an origin here, and say we had a point mass here, call it m, then the moment of inertia of this point mass from that origin is m times this distance squared. Just like that, let's say we had another mass. Let's say we had a second mass here. We'll call it m2. So this is m1, r1, and now m2 is at a distance r2 away from the origin. Sorry, that square shouldn't be there. Okay, now, so for 2 point masses, we have I is equal to m1 r1 squared plus m2 r2 squared. Similarly, we can do this for an arbitrary n number of point masses with distance r sub I and masses m sub I. So for n point masses, we have the moment of inertia is the sum from I equals 1 to the number of point masses of m sub I r sub I squared. Now, okay, so that's what it is for point masses. If we were to take this to the continuous case where we're talking about some object, so say we have our origin here and we have an object like so that has that has mass big M, and we wanted to find the moment of inertia of this big mass, a continuous mass M. How would we do that? Well, just from the formula for the moment of inertia of n point masses, for a continuous mass, the sum would turn into an integral, and it's an integral over the mass dm, so it's over tiny little masses that make up this larger object times the radius squared. So what that looks like over here in this picture is, if we take this really tiny mass dm, it behaves very much like a point mass because it's so tiny and it's at some distance r, and we just integrate over dm r squared to get the moment of inertia. Okay, so that's the formula for the moment of inertia of a continuous mass. Let's try applying this to an example. So the example we're going to look at is a cylinder. It's a uniform solid cylinder. What does that mean? Let's take a cylinder that looks like this. Let's say it has some height h and radius, we'll call it a, radius a. And let's also say that this cylinder is of uniform mass density rho. The mass density is just It's just dm over dv, the differential mass over the differential volume, and that's a uniform quantity, so it's constant. And the question is, what's the moment of inertia of this cylinder about the axis that goes right through its center? So to answer this, we'll first write down I equals the integral of dm r squared. And now we want to relate dm to this variable r, to the distance from the axis in this case. So the way we're going to do that is we're going to use rho because it's dm over dv. We note that because rho is dm over dv, we have dm is equal to rho dv. So this integral becomes the integral over rho r squared dv. Okay, now what's dv? Let's look at a bigger picture here. So we have this cylinder. It's got height h, and we want to find its volume element, dv. So the way we're going to do that is we're going to look at concentric sub-cylinders that make up this larger cylinder. And we can consider these really tiny sub-cylinders with volume where, they're basically these rings that you extend in the horizontal direction, so it gives you this hollowed out three-dimensional cylinder, and concentric pieces like these make up the larger yellow cylinder. So the volume of each of these pieces is the differential volume dV of our larger cylinder. Why? Because we have dV is equal to the volume of this green cylinder. It's going to be given by h times the area of these rings. It's a differential area because it's an infinitesimally small quantity. Okay, so we have dV equals h times dA. The question is, what's dA? Well, the area of a disk is pi r squared. So we have that dA is just d of pi r squared, and differential elements of the area of a disk give us the area of this ring. So it's going to be pi h dr squared, and dr squared is just 2 times r, so we have 2 pi h r dr. Okay, so that's the differential volume. Now let's place that into our integral. For I, we have the integral over rho r squared dv. dv is given by this quantity here, so we get 2 pi h rho r cubed dr. Integrating through from 0 to final radius a, we get that this is equal to pi over 2 times h rho a to the 4th. Okay, so that's the moment of inertia of this cylinder. Now, we can go a step further and simplify this by noticing that because rho is constant, it's equal to the total mass of the cylinder divided by its total volume. And so the volume of the cylinder is just pi a squared h. So we have that I is equal to pi over 2 times h times rho, which is this quantity, times a to the 4th. And we get some nice cancellations over here, and this gives us 1/2 m a squared. And so finally we have that for a cylinder of radius a that's solid with uniform mass density, its moment of inertia is 1/2 m a squared.
I hope you guys enjoyed that video. If you did, give it a like, subscribe to the channel, and I'll see you all next time.